So now let's talk about rotational inverses. And the way that we're going to do so is we're going to look at what happens if we look at a vector from 2 points of view. So typically, you may have seen a vector written in the x and y coordinates, which makes sense. We use the x and y coordinates all the time, and they're very convenient. We say that there's one coordinate going across, one going to the right. But now let's say that you're on a slope. Rather than worried about straight up and down, you might want to go tangent to the slope or the hill that you're on. So we could say that we have x prime and y prime, where that's just another way of viewing a vector. You can view it in the xy coordinates, or you can view it in the x prime, y prime coordinates. So let's go ahead and draw ourselves a vector. And one other common term we'll use is phi, where phi is the angle between x prime and x, and conveniently, since we have that phi plus whatever angle is between x prime and regular y is 90 minus phi, and then x prime and y prime are 90 degrees apart. We also have a phi on this side. It doesn't really come into play, but just to remind ourselves some rules of triangles and angles as we go through this analysis. Now let's go ahead, draw ourselves a vector, and we have the vector s, and we'll give a little hat to let us know it's a vector. And we can look at vector in the xy coordinates. So if we are looking at an x and y, we might break it down to saying that there's an sx component and there's an sy component. The other way we could do is we can say that, well, let's look at s from the s prime point of view. And if we do that, then we'll have s prime x and give it prime s prime y. And here you can see that my right angles are a little wonky, but assuming that all the right angles where I draw them are right angles. So we have our s prime x, and what we want to do is eventually get ourselves a way to transform from one vector to another. So if s prime x, if we want to project that onto the x plane, we can see that it creates a hypotenuse of a right triangle that has a angle phi. And s prime x times cosine of phi can be on the horizontal. For this vector s, we see that s prime cosine phi is slightly longer than sx. But let's see how sy comes into play. So if we look at sy, we see it over on the right, but let's transform it over. And if we move that transformed over, we would say that sy is that line drawn in red there, and because we have phi would be phi minus 90 in that corner, we can do some trigonometry to find out that phi is also the angle there. So sy cosine phi happens to be the exact distance between sy sine phi is the exact distance between sx cosine phi minus sx. Or, another way that we write it, and another way that we will write it, is that sx is equal to s prime x cosine phi minus s prime y sine phi. We can do a similar analysis looking at our sy. So we have sy as that horizontal line in blue, and if we look at the top part of it, we can say that that can be described with our s prime y, because the distance from that edge is going to be s prime y cosine phi, and the height at which that dark blue line starts is going to be at s prime x sine phi. And so the book also has some drawings, so if this did not make sense, that's okay. The key takeaway is going to be this equation. Sy is equal to s prime y cosine phi plus s prime x sine phi. And the reason we just talked about sy cosine phi and s prime sine phi in that order, but if we want to put this in a matrix format, we're going to want to be consistent with when we use s prime x and s prime y. So if we want to put this in matrix format, let's have the vector s of s represented as sx and xy. That'll be equal to our A matrix times s prime x, s prime y. Another way we can reference this is our S vector is equal to our A matrix times our S prime vector. And that A matrix we're going to talk about as our rotational matrix.